Hey guys, so before we get on to nice normal differentiation, we're first of all looking at differentiation by first principles. Now, first principles is basically how differentiation came to be, so it's sort of the maths behind the magic. Now in your exam papers, sometimes you will be asked to differentiate from first principles. Most of the time though, we'll be doing what I call nice normal differentiation, which is a lot simpler. So this video is, if you like, the proof of the derivation of first principles, and in the next video we will do some examples. So differentiation is all about finding the gradient of a curve at a certain point. So that's exactly what differentiation from first principles is about. So let's crack on and have a look. Okay, so as I just said then, differentiation is all about finding the gradient of a curve. So we're going to be dealing with a curve that looks like this. Now, the mission is to find the gradient of a curve at a given point where the x-coordinate we just write as x, and the y-coordinate, well, we write that as f of x. So what's going on there? So we say that our function is just something of the form y equals f of x. So we choose a point along the bottom, so along the x-axis. Now we're going to say that has coordinate x. Now the y-coordinate of that, or the y-coordinate there, the y-coordinate on the curve at that x-coordinate is given by substituting the x value into the function. So we get f of x. So what we can also find, as well as finding the gradient at this point, we can also find equations of tangents and what are called normals. There's quite a lot of stuff we can do with differentiation. In this video though, we're just going to worry about the gradient. So the reason I've got a tangent here is just to remind us that a tangent is a straight line that hits a curve at one point and one point only. So to derive differentiation from first principles, we're going to be looking at chords. So let's have a look at those. Okay, so remember that a chord is a straight line that hits a curve at 2 points. So here we've got a chord drawn. Let's zoom in and see what's going on. So we got y equals f of x again, and we have our original point with x coordinate x and y coordinate f of x. Now we got this second point along the line to the right, which has x coordinate x plus h. Now h is a tiny amount, so here imagine we're zoomed right in on our graph like 1,000 or 1,000,000 times, so h is a teeny tiny amount that we've gone along the x-axis. So at this second point, our x-coordinate is x plus h, and then our y-coordinate is the value of the function when x is x plus h. So when the x-coordinate is x plus h. So the y-coordinate here is f of x plus h. So what we're going to do is we're going to see what happens as h gets smaller and smaller and smaller and smaller. So we're going to see what happens to the chord. At the moment, we can see that this red chord is not a very good approximation of the gradient of the curve at our original point with coordinates x, f of x. It's a lot steeper. So what we're going to do then, we're going to see what happens as this already tiny amount h gets smaller and smaller and smaller. So now I've taken away the axes. We don't really need the axes. This is just somewhere on our curve that we zoomed right in. So I've drawn some different chords here with different sizes of h. So the red one is with our biggest value of h. Then we got the blue one, h is a little bit smaller. So already, can you see what's happening? The gradient of this chord is decreasing. Now we can see the gradient of the curve at our original point x, f of x, it's quite a gentle one. So with this decreasing gradient, it's tending towards the gradient of the curve. Then we decrease h even more, so we can zoom in as well. So now we've got this green chord, which is even closer to the gradient of the curve. It doesn't really span very far, so now we've got a really small value of h. If we make it even smaller, so if we now look at this orange x plus h, we can see that this orange straight line pretty much just goes along the curve. When we've zoomed in this far, the curve between these 2 points is pretty much a straight line. So this chord gives us our best approximation here at the gradient of the curve, because h is as small as possible. Now, if we keep decreasing h, we're going to get closer and closer and closer and closer to our original point that had x coordinate of x. So what's going to happen, the smaller that h becomes, the better our approximation of the gradient of the curve. So now we're going to use this side here with a bit more coordinate geometry to show our expression for our formula for the gradient of a curve. Okay, so we need to remember that to work out the gradient of a straight line, if our coordinates are x1, y1 and x2, y2, then the gradient of that straight line is y2 minus y1 over x2 minus x1, or the difference in y over the difference in x. So now we can apply that to our coordinates here to work out, first of all, the gradient of the chord and then the gradient of the curve. Okay, so if we now apply that to our coordinates, so we know our 2 points are x, f of x, and x plus h, f of x plus h. So the gradient of our chord then is f of x plus h minus f of x, the difference in our y coordinates, over x plus h minus x, the difference in our x coordinates. So we can simplify that a bit. On the bottom, x plus h minus x leaves us with h. So the gradient of these chords is f of x plus h minus f of x all over h. But that's going to give us the gradient of a chord, not the gradient of a curve. So how do we now use this to find the gradient of a curve? So we can't just set h equal to 0, because then we'd be doing one of the biggest no-nos in maths. We would be dividing by 0, which we are not allowed to do. How do we get around that then? Well, remember a couple of pages ago when we had the curve with some different chords drawn on it? What was happening, our value of h was getting smaller and smaller and smaller. Now what was happening, that second coordinate point was getting closer and closer and closer along the x-axis to our original point x. X plus h was tending towards that point x. Now what was happening there to h was it was getting smaller and smaller and smaller. What we could say is that h was tending to 0. So the gradient of the curve is given by dy over dx is equal to the limit as h tends to 0 of f of x plus h minus f of x over h. So we can't just substitute in h equals 0, but we can say as h tends towards 0. So as something tends towards 0, it's getting smaller and smaller and smaller. So as it gets infinitesimally small, you can sort of ignore it. Now we're going to see how that works in the next video, where we go over some examples of differentiating by first principles. Hope this has helped, guys. See you there.